is where, to me, the fun part starts. So this is kind of that's the end of like the required material for chapter 5. What I want to do now is kind of, you can effectively just sit back and relax. I want to try to explain to you where that came from, just to kind of demystify Newton a little bit. I mean, he was 23 when he came up with that, so he is kind of a genius. But once we have his 3 laws of motion, that's what the whole idea is, that he came up with those 3 laws of motion in order to get that. It wasn't, he didn't come up with the 3 laws of physics just so that we can do problems for a semester of mechanics. And he also, this is the main part of how physics works, is he looked at other results, people who did things before him, and tried to figure out how he could use his laws of motion to match up with that. And then what we're going to do at the very end is poke holes in it, because it turns out that Newton is not the one who actually understood how gravity worked. And we'll see why in a little bit. And then in recitation, I'm going to start us off with a big sheet of spandex, and we're going to play around with it and try to figure out how Einstein fixed it before we get to some chapter 6 examples, just to kind of prep stuff. Okay, so let's start with the story. You may know the story. The story is that Newton was sitting outside trying to figure out how the moon kept going around the Earth. He was trying to figure out how the moon could just keep staying near the Earth instead of just flying away. And he saw an apple fall. And as soon as he saw that, he thought, okay, maybe the moon is falling towards the Earth. It's just traveling constantly. It's constantly being pulled through the Earth. And so we know that that is definitely some acceleration, right? Because that's a centripetal acceleration. It's going in a circle, even if it's traveling at the same velocity. So that means there's an acceleration. So if something is accelerating, that means, by Newton's first law, it has to have some force. So if there is an acceleration, there has to be a force. And that's what Newton first thought of. He said, okay, there's got to be a force. How about I start, instead of thinking about some net force or some random force, how about I write this equation for gravity and try to figure out if I can do anything with that. So the first thing that he did with his second law, he said, okay, I know that F equals ma. So I'm going to write the force of gravity is some mass. It could be the apple falling, it could be the moon orbiting the Earth, or, as we'll talk about in a little bit, the Earth orbiting the sun. And now he'd need to figure out what the acceleration is. This is where the apple came into play, because that reminded him of some work that some other people have been doing, notably Galileo, who I'm fairly certain died exactly on the year that Newton was born, so they're not that far apart, believe it or not. Galileo was the one who told us that all objects accelerate at the same rate. So we didn't know at that point that g was 9.8, but they knew at least that the objects are accelerating at the same rate. So that tells us, regardless of if it's an apple or a bowling ball or anything, the a, at least, is a constant. So this is where Newton wrote this. So we have the force of gravity is the mass of the object that's experiencing it, and some constant value. And this is where the stuff that we did on Monday, where we said, like the spring force. When we were looking at the spring force, we wrote something like this. I wrote a proportional symbol. So the way that we reasoned this out was, if I push on the spring in that direction, so let's say to the right is positive, we know that the spring is going to push back on us, so that's a negative. So in order to have those two things being proportional to each other, we're going to include that little negative sign. And the reason we wrote it like that was because there is no other dependence. It only depends on how much you smush the spring or stretch the spring, and then that negative to flip it over. So the main thing about this whole proportional math stuff is that you can go back and forth between these two equations. So I can either say the force of a spring is proportional to how much I squish it, and then I reverse the direction of that squish, or I can say it's equal to some constant, which tells me about how strong the spring is, or something like that. So this is actually, I'm kind of pleased that it's in the textbook. I forget it's in there every year, because it's not something usual that's in textbooks, this whole idea of using proportionalities in physics. So it's in the textbook around the like 5.4 mark, and the whole idea is that if you have some relationship between variables, so u is proportional to v, you can also write that exact same proportionality as equals a constant and the variable that it depends on. So in terms of that equation that Newton had with Galileo's revelation that all things accelerate at a constant rate, that means that Newton can write this, that the force of gravity is at least dependent on the thing that's doing the falling. And this is where his third law came into play. Because if the apple is being pulled towards the earth, technically, if the third law is true, the earth is also pulled towards the apple. It's just that the earth is so much bigger, so we don't see that acceleration. So that means if this force of gravity is also dependent on the earth, then he can write, not only is it proportional to the little mass that falls, but it's also proportional to the big mass that's causing the falling. So one additional thing about these proportionalities that the textbook doesn't cover is if you have two of them, so we've got two different things. The force of gravity is proportional to little m, and the force of gravity is proportional to big M. If you ever wanted to combine things like that, you just multiply them. So if you ever have two proportionalities, you now know that that object is proportional to the product of those two things. So this is pretty close. If we think about Newton's law of gravity, we've got G equals m over m r squared. So effectively what we're trying to do, and this is how Newton did this, is he was trying to prove that it was proportional to those things instead of equal to them. The whole, his big G factor didn't come into play until way later. We'll talk about that. So we've got the numerator. We've already done that with just Newton's first, second, and third law. Now we need to figure out that. So we're effectively trying to say that the law of gravity, or the gravitational force, is proportional to 1 over r squared. Because if we have all those three proportionalities, we can combine them in a product and say that that's actually true. This is where Newton had to look backwards. So Galileo was one way he looked backwards. Now he's going to need to do some more deep diving. And this is where his kind of genius came into play a little bit, because the next thing that he used doesn't seem to relate to anything that we've been talking about yet. This is something that was discovered experimentally. Johannes Kepler was an astronomer, and when I say that this was discovered experimentally, that basically means that Kepler had a big table full of a bunch of r values and a bunch of t values, and he just tried to put them together into random ways in order to find some relationship between them. So in this equation, t is the orbital period of a planet, so like for us it's 365 days. And this is the distance from the center of the rotation, so the sun, to whatever planet he's talking about. So all the data he had, it just looked like a big table like this. This is very old data where they were using a method of parallax, it's called, with the telescopes. So these numbers aren't exactly what they are in reality, now that we know we have better telescopes. But he just had this table. He didn't have this column at all. He said, there's got to be some relationship between these things. It was the 1600s. They were bored back then, so he just started making ratios between these things. And he discovered that the ratio of the period squared over the radius of orbit to the cube is actually a constant number. So these are some old data. If you look at modern day data, those are almost exactly the exact same. So that was close enough for him to say that this is some constant value. So that was weird, and the more that this came about, more people started to get into astronomy in this kind of golden age of science, and those numbers just kept getting closer and closer and closer. So by the time Newton was doing his work, that was something that had to be true. So he said if the apple is falling, that's probably due to this gravity that he was trying to envision. The moon coming back towards the earth, that's gravity too. Maybe the sun orbiting, or the earth orbiting the sun, is also gravity. So this is where he was trying to use Kepler's law. And the next thing that he used was this, the centripetal force. Does anyone know how to pronounce that? It's if you ever seen it in high school, the buoyancy, the fact that rubber ducks float on water. Usually it's called Huygens principle. I mean, this whole derivation is just me being a nerd, so I figured I might as well just go full nerd on you. The way to actually pronounce that, it's not Huygens, it's Huygens. So this, the cool part about Dutch is that like a lot of English is just Dutch written differently. So for instance, the word out, it comes from the Dutch word out, which is pronounced exactly the same way. So out. And this O-I, or U-I, is just kind of the modern way that Dutch people say U-Y. So this pronounced is how, and then the G is like kind of in the back of your throat, like k, so happens. Anyway, it's like the whole derivation is me just adding stuff to chapter 5 anyway, so I might as well add some fun stuff. And we don't really need to do anything deriving this, right? Because if we already know that the centripetal acceleration, we spent a bunch of time deriving that. We didn't mention this guy by name when we did that, but all that similar triangle, adding all the angles to 180, we figured out that the centripetal acceleration was v squared over r. And if we just plug that in to Newton's second law, we can figure out what the centripetal force is. So it ends up just looking like that. And we can do one thing here, and this is where Newton started to realize, let me try to make this look like, at least have the same variables as Kepler's third law. So Kepler's third law didn't have a v in it. It did have an r and a t in it, though. And if we're talking about orbits of planets, then the velocity is just going to be the circumference. It's how far the orbit goes, so all the way around the circle. And the time it takes is the period. So now r and t are in that equation. So if we plug that in to the centripetal force equation, then it's going to end up looking something like that. So we plug that in. We're going to start just rearranging some stuff. We've got a fraction inside of a fraction, so that looks weird. Let's bring that r over here. And now we're just going to start distributing. We've got a v squared, so we need to square everything that's over there. So we've got a 4, pi squared, an r squared, and a t squared. So it looks like one of those r's is going to cancel. So we end up with this. One of those r's canceling, and that's our final result. Cool. Okay, so that is the force of centripetal acceleration. What Newton thought was, at this point, all the church zealots had already done the work of convincing people that everything isn't orbiting around us. We are orbiting all around the sun. So at this point, Newton said, okay, let's try to think that the centripetal force, the thing that's causing things to keep going in a circle, maybe that's gravity too. Kind of like the apple is pulled towards the tree, or towards the earth. If that's the sun, and all these planets are being pulled towards the sun to be able to move in a circle, maybe the force of gravity is just going to take the exact form of the centripetal force. And this is where he started to say, okay, there's got to be a way that I can make this work with Kepler's law. Kepler's law at this point was decades into success. Everyone believed it. So he knew that his theory had to agree with Kepler's law. So the way that he did this was he started to rearrange this equation until it looked like this. So this is an equation that says equals a constant. Are there any other constants up here? There actually are. And the numbers, you may think like 4 and pi squared, but if we're talking about planets orbiting, then the mass of that planet, unless it's struck by an asteroid or a giant volcanic explosion, the mass of that planet is probably going to stay relatively the same. So m is a constant. 4 is just a number. That's a constant. Pi squared is just a number squared. That's also a constant. So that means all those things over there, other than the r and the t squared, are constants. So let's try to rearrange that equation a little bit. We're going to bring the t squared over here and then divide by the r. Because then everything on the right-hand side is just going to say equals a constant. So now that's starting to look a lot like Kepler's law. And that's where Newton got excited, because that told him that the force of gravity has a requirement on it. In order for those two equations to be true, there's only one possibility. The force of gravity has to have a 1 over r squared in it. Because this, if it's going to end up equaling that equation, this thing has to have a 1 over r squared, so that there ends up being r to the third. And that was it. That was all he needed. Now he has that the force of gravity is proportional to little m, the thing doing the falling that we can observe, the big M that's causing the gravity to happen, and the r squared. So now we've got three different things, multiplying all three of them together, and we end up with the final equation. So that's how Newton derived that. Not so crazy once you see that all his laws kind of together with Kepler and Hawkins' centripetal force, they actually do make sense. So one thing before we get to what's wrong with that, let's just take a look at that value g, because it took even longer for people to figure out what that was, because remember how small of a number it is. It is an insanely small number, and the way that they did this was over 100 years after Newton actually did all this stuff, was they hung masses from a wire. And they didn't have, even at that point, they didn't have vacuum chambers or anything like that, but they did have methods to control pressure and make sure there's no wind throughout their lab room, and they just left it there for a long time. And they eventually saw that these objects were rotating towards each other. And so they used a bunch of measurements to figure out how much force was exerted between those two objects, and used Newton's law of gravity to figure out the constant g. So that constant g, you can call it a force constant. It's how strong that particular force is, the force of gravity. And all of the different forces have that. So all of them, the gravitational force, the strong nuclear, electromagnetic, weak nuclear, they all have their own version of g. And one way that we can get another intuition about why it's so hard to get gravity to mesh up with these other forces is how small that number is. So just as an example to figure out how small that number really is, let's calculate the forces for a regime where all of them act. Notably, these two are really only going to be present when we're talking about inside of an atom. So if we let r be really, really small, we're not talking about planets anymore or big macroscopic objects. If we let r be like the radius of a nucleus, just something insanely small inside an atom, then the strong nuclear force, the thing that keeps all those atoms together, is going to be the strongest force. And that force is 100 times stronger, 137 times stronger than the electromagnetic force. These things are all kind of charged particles, so they definitely have an electromagnetic force. We're talking about inside the atom, so we've got a weak nuclear force. It's 1,000,000 times stronger than that. And there's not even an English word to say for 10 to the 38. 10 to the 38 is a lot of zeros, so that's another reason why the gravitational force is so hard to get to map onto all these other forces. The whole theory of everything is really hard to get these things all to work together because they're on very different scales. Okay, now what we're going to end with and what we're going to start with on Friday is what's wrong with it. So that equation, Newton knew something was up with it. Einstein was the one who really poked the hole in it. So Einstein, he has a whole Wikipedia article based on all these. He was famous for his thought experiments, or Gedanken experiment in German. His thought experiment to poke a hole in Newton's theory was, what if the sun disappeared? Because if the sun disappeared, then suddenly there's no big M in that equation over there. Big M just becomes 0, and now there's no more force. And we immediately shoot away from the sun. And that's an issue, because there is none of these variables depend on time at all, which is kind of crazy. So that means that if the sun disappears right now, we will immediately, we'll all smash into the wall, but the Earth will just shoot away from It's like cutting the rope on someone doing like a hammer throw or something. And that's an issue. The issue is Einstein was doing all these thought experiments around 1915 when he was kind of coming up with his theory of general relativity. But 10 years before this, he was, won many, many prizes for the theory of special relativity, which the main result of that was that there's a speed limit to the universe. The speed limit to the universe is the speed of light. So that's why this is an issue, because if that's the sun and that's the Earth, the speed of light has a very, very well-known value. It is 3 times 10 to the 8 meters per second. So that's not that big of a number when we're talking about the distance from the sun to the Earth. It would take about, I think, 8 minutes. It would take 8 minutes for light to reach us. So if the sun disappeared, we would still see it shining in the sky for 8 minutes. So it's impossible for information, notably like gravity, we would still feel the force of gravity for 8 minutes before we shot off. So that was the issue. We need to figure out some way, and this is what Einstein was famous for, to put time into Newton's law of gravity. So the first thing we're gonna do, I'm gonna show up with some big spandex sheet, we're gonna stretch it apart and do a bunch of stuff and try to figure out what was wrong with it. Because even Newton knew that there was something wrong with it. This is some old primary source, a letter he wrote to his friend where he said, this is impossible. You can't just have some change all the way on the other side of our galaxy and immediately feel the effect. It's something called non-locality. You can't just have something on the other side of the universe magically happen and then we experience it. So he had an idea, even hundreds of years before Einstein came up with the speed limit, that you can't just have things happen instantaneously. So that's what we're going to do on Friday. We are going to bring in a big spandex sheet. So try to think of, why am I saying a spandex sheet? What does that even mean? So what we're going to do is try to figure out how Einstein changed Newton's law to actually get with the main law. And then we'll just do, we are going to have our weird recitation because, well, one, I have to finish being a nerd. And then we're basically, there's not a lot of chapter 5 stuff. The only homework problem that you have to do is that one with the slopes. You have to figure out the slope in order to find the acceleration or the mass. But overall, we're basically, after we finish this my nerd out, we're just going to do some kind of prep work for next week with chapter 6. So we're just going to do some examples of chapter 6, not kind of typical recitation style. I'm just going to do some examples for you, just to get us prepped about what we're going to be seeing in the next few weeks. Before that, let me finish being a nerd. Okay, so what did we discover when we thought about Einstein's law of gravity? I need a marker. So Einstein's law had a form that did not allow for any time to happen between the force of gravity. So for instance, if we drew the sun as this big capital M here, and the Earth was a little m on the outside, then, well, what did we do when we looked at Einstein's law of gravity? We kind of demystified him a little bit by looking at all the other stuff that he used. And we'll do that with Einstein today. It just turns out that whereas Newton used Galileo, Kepler, and centripetal force, Einstein used differential geometry, which is an insane topic. We would need a whole course to even start getting started on it. But that's what the spandex sheet is for. So we don't have to learn differential geometry to appreciate Einstein's law of gravity. So Newton had this, and the issue here is that if the sun disappears, suddenly it becomes 0, and the whole force becomes 0. So that means immediately the Earth just shoots off. No bueno, because Einstein said 10 years before his theory of general relativity, his theory of special relativity said that there's a speed limit for the universe. The speed limit of the universe is the speed of light. There's a special symbol for that, and it's a very well-known quantity, 10 to the 8th meters per second. And remember, when we were doing the, like, is the Earth an inertial reference frame, we had that distance. It was like 150 million kilometers. That was like 10 to the, I think it was 11th, 13th or something. I think it was 13th. So it's going to take some time for that speed, for the light to get from the sun to the Earth. So if the speed limit for the universe is that speed of light, then even the information about the sun disappearing, the gravity changing, it's going to take time to go over there. That's what Einstein was after. And even Newton knew something was up. His kind of letter to his friend, whispering, don't tell anyone my theory's bogus. He knew that this was impossible. It's impossible for an object disappearing on the other side of the solar system to immediately affect us. It's 150 million kilometers away. So how did Einstein resolve this? Einstein tried to figure out a way to put speed into this problem. Some way for us to allow basically slowing down the information about gravity. How is he going to allow some time for this disappearing to reach the Earth and for us to feel it? The way that he did that, without going too much into differential geometry, is revealed through this sheet. So I need at least 3 people to grab onto the corners of this thing and pull it super taut. We can have 4 if everyone wants to get involved, but at least 3 people to grab onto the corners of this thing and pull it really hard. It is so fun.
Do it.
Oh.
First people there, first 3 there win.
Go.
Yeah, grab a
We have
corner.
4.
Oh, sweet, we got 4. The first section I've got 4. I've had the whole corners. Okay, pull it as hard as possible. Okay, so the first thing we're going to do is we are going to forget about big capital M. This is going to be the big M. This is going to be the thing that's causing, making these objects, the little m's, feel some gravity. But before we talk about gravity at all, what we're going to do is just think about this object rolling along the surface of the universe. This is basically going to talk about the surface of the universe. So if the surface of the universe is, in this case, it's just flat, right? So if I roll a ball along this flat surface, if it rolls off, it's fine. That's a straight line, right? And the object traveling in a straight line, the straight part of that isn't special. What's special is the object traveled in the path of least resistance. So that means if I include the m like that, this object is still going to travel along the path of least resistance. And this is where it gets weird, because technically this is also a straight line. The idea is that the definition of straight depends on what the straight line is. So in this case, a straight line, the word straight, just means the path of least resistance. So this is not responding to a force, it's just traveling like water. It wants to go as easy as possible. And that just happens to be a straight line when the surface is curved. So we'll talk a little bit more about that, but in the interest of everyone's biceps, so they don't have to keep doing this all day. Now, what we're going to do, I can't really take that weight off very quickly, but what I can do is pinch this, and imagine that is the weight that I was just holding. And let's do a demo about Einstein's predicament with Newton. If the Earth or the sun just disappears, it needs some time for the information to go from my pinched finger to everyone else's hand. So everyone else's hand can represent like the Earth. If I let go of this, imagine like a slow motion picture of this. The thing rippled, right? It took some time for this to ricochet outward and spread across. So that spreading of information is what Einstein was so happy about as soon as he started talking about the universe as something with some structure. Okay, that's basically the demo. Thank you very much. We will talk a little bit more about what the straight line business was, because that may be something that you've seen before. So this is what we just saw. when there was no big capital M in the universe, the object just traveled in a straight line because that was what the path of least resistance was. But as soon as we introduced some big capital M, the structure curved, and what a straight line was changed. So one way that you may have seen this before, even from the first time I was on a plane, I had an iPod or something that I could entertain myself with. I never used the little games on the back of the seat, but something that I did see on the back of the seat was the path that the plane was going. And if you look at it on a map, the path that the plane travels is not a straight line because the Earth is not a flat surface. It's a curved surface. So the distance when you go between two different locations, this is just some random picture I found. I don't think most people are going to Moscow nowadays. That is a much shorter distance than a straight line on 2 dimensions because the Earth is curved. So another way that you would see this, a lot of things that we were using in chapter 3 relied on the angles of a triangle adding up to 180, right? If I put that triangle on a curved surface, the angles don't add up to 180 anymore. That's kind of another example of this the thing that Einstein was using, like he went backwards and looked at what other people had done. He actually just looked at mathematicians' work. So this whole idea that math changes when you start curving your surface, that's what differential geometry is. So that's what Einstein utilized. He said that the Earth, or the universe, has some structure, and the presence of mass curves it, and that's what all the other mass responds to. So this is also going to resolve this big issue. Because if I pinch, I bring down the surface of the universe because there's mass in it, and then let it go, it's basically like a rock dropping in water. It's going to take some time for the ripples of the universe to travel all the way over to whatever the system is that we're looking at, the orbiting Earth. So it's going to take time for that information to spread across. And that is going to obey Einstein's speed limit to the universe. So this whole idea that it's going to take time now was what Einstein was so happy about. And another way to talk about these ripples is in terms of waves. Right? I can think about it as a ripple, or I can think about this information that the gravity has changed as a wave that kind of goes across the universe. And that word, gravitational wave, may be familiar to you because gravitational waves were very weirdly, Einstein's theory of special relativity was 1905, his theory of general relativity was 1916. Exactly 100 years after that, it was discovered that gravitational waves do actually exist. The way that it was determined was not, I don't think the sun disappeared in 2016, but what ended up happening was really far away in our universe, 2 black holes, you can kind of think about them as these big plates that we saw curving the space-time, they started to get close to each other. So much so that they started orbiting each other. And imagine if we had 2 of these plates going around the spandex sheet. Things would start to look really weird. And so those ripples propagated throughout our entire universe, and we actually detected it. Laser, I think LIGO stands for Laser Interferometer Gravity Observer. You may have seen me look up when I said that, because as you leave the class today, you'll see the letters LIGO on a poster right there. The next slide, I kind of debated putting it in this year, but it's important. The reason there are these posters outside all the time, the Nobel Prize really can only be awarded to 3 people, but this LIGO effort was worldwide. And we had you can't really talk to Einstein anymore, but last year I would say, as you leave, look at that poster right there, that we have a genius right down the hall who worked on this stuff. Unfortunately, Professor Struver passed away last year, but she was the best. She would do this demo all the time, and I just think it's important that I mention this because she was like a actual modern day genius who worked at Villanova. There are a million posters that with students that she worked on this stuff with. And just to kind of give an example of how impressive she was, 18,000 citations is insane. Just to give you some context, I'm super proud that my thesis has 7 citations. And just like some other professors here, just some random professors I picked, have like hundreds of citations. So Amber having 18,000 citations was just wild, and it was so cool to be able to say like, yeah, there's this real history of this work at Villanova. So I just wanted to include that. She would love this demo still, so I wanted to make sure it was, pointed it out. So let's summarize what we learned here. What we're going to do is we are going to use a quote from one of the biggest kind of authority texts in this field. It's like the gravity Bible is what people call it. It's giant. It's its own source of gravity. It never leaves my house because I just don't want to bring it to the office. It's so big. This guy was the PhD advisor of these 2 people. We'll talk about this one in just a second because that guy was one of the 3 who won the Nobel Prize for this. And basically the reason, the Nobel Prize they have to have only 3 people at most who win it, and he was one of the ones who thought up the experiment, so they gave it to him. This guy, instead of thinking about, if I were to write out Einstein's equations, you would run and hide because there are just so many crazy symbols in them. He summarized it in English very, very well. So big M, the thing that we saw in the sheet, that tells the space-time, and space-time is basically a word that Einstein used to talk about this structure of the universe. This is space-time. It's our universe. So matter, or mass, tells the space-time how to curve, and then, once it has been curved, the mass, the little m, just follows that curvature. It now knows what the path of least resistance is, as it has that curvature. So very kind of simple, boiled down way to talk about Einstein's theory of general relativity, or GR. I think it's cool to mention this person. Not only did they win the Nobel Prize for this, envisioning this LIGO experiment, but if you look at the wording of this, the kind of Wikipedia, scientific consultant and executive producer. So not only was this person a Nobel Prize winner, they actually work on movies. Interstellar has scientific papers written about it because of how accurate it is, because Kip Thorne worked on it. So all the scenes in Interstellar and actually the math and people analyzed it. There are entire classes on the movie Interstellar because of how accurate it is. This guy basically wrote the book on black holes. So the idea that a lot of that movie is actually incredibly scientifically accurate is just pretty cool. Okay, so that kind of finishes up my nerd out of chapter 5. The whole reason for this was we don't get to chapter 13 in the course, so I thought it would be cool to just talk about all the stuff that we would have been talking about if we got there. Chapter 5 is kind of like. Okay, so what we're going to do now, still kind of weird